Hi, welcome to Gases 1. Today we're going to talk about pressure and begin learning about the gas laws. So let's get started. So a gas, let's talk about the properties of a gas. So gases don't have a definite shape or volume. And if we look at gases, they expand to fill the volume of the container that they're in. And so if you put gas in a container, like for example, if you put helium in a balloon, it's going to fill that container completely. And if we take a sample of anywhere in that balloon, the helium atoms will be distributed the same throughout. Now, if you took that helium and you put it in a bottle filled with air, the same thing would happen again. It would begin to even out and distribute throughout and expand to fill the volume of the container, and it's going to mix. It's going to form a homogeneous mixture with the oxygen and the nitrogen and the carbon dioxide that's in our air. Now, another characteristic is that there are very few particles per unit of space in the mixture. And so gases have a really low density. In fact, if you look at a gas, if you look at the air in the room that you're in right now, 0.008% of the air in the room is really just empty space. This is the amount of the air in your room that's actually filled with particles. The rest of it, 99.99%, is actually just empty space. So this is not true for a liquid or a solid. Liquids and solids take up about 70% of the overall volume of a substance, but air, very little. Now, because of this low density, they also have the property of being highly compressible, meaning you can take air and you can compress it and put it in a cylinder. And so doing this, you dramatically increase the density of the particles. Another property is that they exert pressure on their surroundings. In other words, you have particles of a gas and they're moving, and what happens is they actually collide with the containers, with your body, with everything around them, and produce a pressure. So this is the basic formula for pressure. You do not have to memorize this. This is just to kind of give you an understanding. But every atom is bouncing off of a surface. And whenever an atom of a gas, like oxygen or nitrogen or helium, hits something, it applies a force. And when it does, it produces something called pressure. Now, if we look at the relationship between pressure, force, and area, if you step in a puddle of mud, you'll sink. You apply a certain force. But let's say instead of sinking, you put down a big sheet of plywood on that puddle of mud and you step on the plywood. You greatly increase the area. So when you step down, you apply the same force, but you increase the area, which decreases the pressure. And so that's kind of a little quick, sidebar on the relationship between pressure, force, and area. But gases exert a pressure by bouncing off of surfaces, and what happens is, since they're evenly distributed throughout the container, the same number of particles smash against every square centimeter every second. And so the force, the pressure exerted is constant. If you keep the temperature constant. If we increase the temperature, we increase the kinetic energy, which increases the number of times that those particles will collide with the walls of the container. Therefore, the pressure is increased. And so you don't really notice the pressure of a gas because the pressure is exerting the force on all sides of you. So, for example, your arm is being pushed down by 1 atmosphere of pressure. It's also being pushed up by 1 atmosphere of pressure. But if we could somehow remove the pressure, pushing your arm up, you would probably not be able to pick your arm up if we have this force removed. So, for example, let's look at a can. If you have a can, there are particles exerting a force on the inside of the can, particles exerting a force on the outside of the can, so the can sits there. But if we apply a vacuum and we start removing the gas particles so that there are no longer particles on the inside of the can pushing it out, only particles on the outside pushing on the can, we can cause the can to collapse. And here I have kind of a dramatic demo of that effect. So here we have a big tank car. Okay. The particles inside that tank car were removed. So there's only the particles on the outside. Pretty dramatic demo of that. Okay. So when we talk about measuring pressure, we generally talk about atmospheric pressure being measured with barometers. And so this is an example of how a barometer works. If you have an open-ended tube, here's a glass tube with an open end, nothing happens. Here we have a big tank of liquid mercury, and the mercury is pretty level throughout. The atmosphere is pushing it down. But over here we have a tube with a vacuum. There are no particles up here. Now you may think that the vacuum pulls the mercury up the tube, but that is not actually what happened. What happens is the atmospheric pressure outside pushing down pushes it up the tube. Over here, there's just a lack of particles pushing the mercury down. And since there's nothing pushing it down, it's allowed to rise up the tube to a certain amount. Now, if you have on the outside, if we have 1 atmosphere of pressure on the outside, then the mercury will go up the tube 760 millimeters of mercury, 760 millimeters high. And so these are ways that we measure the pressure. In fact, up here, this is something that you need to know. If you have 1 atmosphere of pressure, that equals 760 millimeters of mercury. It also equals 760 torr. And this is a conversion factor in case we're not working with the same units of pressure. So let's talk about temperature. We've talked about temperature before, and temperature is the measure of average kinetic energy of an atom. And so if we have the Kelvin temperature, this is proportional to the kinetic energy. In fact, if you double the kinetic energy, our Kelvin temperature will double. And when we talk about kinetic energy, we talk about different types of motion. The main one that we're going to talk about with kinetic energy is translational energy, meaning when those molecules move in a straight line. But it also involves rotational energy as well as vibrational energy. So whenever we talk about collisions, collisions are important with gases. That's how we apply pressure. That's how the volume is affected. But when we talk about kinetic energy, it's always going to be conserved, meaning whenever particles collide both with the walls of the container and with each other, none of that kinetic energy is going to be lost. And we're assuming that, they kind of hit like billiard balls, like pool balls. One hits and then they bounce off of each other. And for example, in this collision, we have one particle moving fast and one moving slow. Afterwards, the green one's moving slow and the red one's moving fast, but the sum of their kinetic energies is going to be the same. So, which leads us also again back to Maxwell-Boltzmann distribution. And the Maxwell-Boltzmann distribution describes the relationship between kinetic energy and temperature. And we can see that at any given temperature, the gas particles possess different kinetic energies. For example, at 1000 Kelvin, there's a large range of kinetic energies for those particles. And so the particles with a lesser amount of kinetic energy at 250 Kelvin will have a lower pressure. If they have a higher kinetic energy, they'll have a much higher pressure. So let's talk about Boyle's law now. Now, Boyle discovered the relationship between pressure and volume. In fact, found an inverse relationship, meaning that whenever the volume is affected by the pressure, if the pressure increases, the volume will go down. Or whenever the volume increases, the pressure will go down. And so, and the converse is also true. So if we look at that, let's look at a picture of that. If we have a container at a certain pressure and a certain volume, if we double the pressure, we're going to have the volume. And so it's a very proportional relationship there for that inverse relationship. And here's a graph of that relationship. We could actually graph that relationship between volume and pressure. And so let's look at a little demonstration of that. Here we have a couple of peeps. So we have Pierre and Marie, and they're learning about a vacuum. And so this is a bell jar in which the pressure inside that bell jar is going to be greatly reduced. There's a vacuum taking the air out.
Two bunnies here. Pierre will be the stunt bunny, he is the bunny inside, and Marie is the bunny outside, so we can look at the size difference between them. Oh, Pierre, I don't know, this could be dangerous. Don't worry, Marie, we'll be alright. Start the vacuum pump. Notice the light in the background. It's making that pumping sound. Oh, Pierre, something is happening, girl. I feel so funny. Oh, Pierre is moving.
Okay, so the pressure is decreasing inside that bell jar. Now, Pierre is full of bubbles, little pockets of air. The volume is increasing dramatically.
There are little tiny bubbles of pressure out there, expanding. Looks like most of the air is out. Probably. Okay, Aaron is now shutting off the tube and disconnecting. Notice his hand in the bottom left so he can't burn.
Okay, so now what they're going to do is they're going to change the pressure inside again. They're going to open it up to where now Pierre is again exposed to atmospheric pressure. And look what happened to him. And so what happened was some of those bubbles inside the marshmallow popped. And so now he's again at the same pressure, except some of those little bubbles pop, so he looks a little bit deflated. So that's a demonstration of that inverse relationship between pressure and volume. So now let's jump to Charles' law. Charles investigated the relationship between temperature and volume. In fact, if you double the the Kelvin temperature of a certain amount of gas, now of course the amount of gas has to remain the same, the volume of that gas will also double. So this one is directly proportional. Now, for this relationship, you do have to use the Kelvin temperature to get that proportional relationship. And so here's an example. You have a certain temperature, which is a certain kinetic energy, and you have a certain volume. If you decrease the temperature, in fact, the the Kelvin temperature is halved. If you have the temperature, you have the kinetic energy. If the kinetic energy is half as much, the particles aren't moving as much. They're not colliding with the walls of the container, so they're not pushing on the walls of the container as much. There are not as many collisions, so the volume is halved. So that's a relationship between temperature and volume. Okay, and if we have to graph that, we would have temperature versus volume, and we'd have a line, and you could actually get data in the lab that would go back to this 0 Kelvin temperature. And at 0 Kelvin, we would have a volume of 0. And so that 0 temperature is known as absolute zero. And this is how they came up with the concept of absolute zero, just by plotting back from known temperatures and known volumes of a gas. All gases will, eventually plot back to an absolute zero. Okay, so you have to know this. You don't have to memorize Boyle's law and Charles' law, but you do have to know the combined gas law. And the combined gas law is not, unfortunately, on your formula sheet, but it's pretty easy. It's PV over T. And if you think of trying to memorize this, if you're not sure about if you can remember which ones go over which one, you always put pavement over a trail. I don't know if that'll help you or not. I'm sure you could think of probably a more creative one. But P1 times V1 over T1 equals P2 times V2 over T2. So if you have an original pressure and volume and temperature, if you change one or more of those, you can find the other. So let's try an example of that, the combined gas law. If you have a cylinder of gas at a constant volume, and we change the temperature from 24.1 Celsius to 326.4 Celsius, and we know the initial pressure is 1.01 atmospheres, what is the final pressure in millimeters of mercury? So let's start and look at what do we know. Well, it says we're at a constant volume. So in this case, our volume before is going to equal our volume after. So that's going to be constant. But we do know we have a change in temperature. We have a T1, which equals 24.1 degrees Celsius. We have a T2, which equals 326.4 degrees Celsius. Now, something that we need to do to both of these, we need to remember, and I'm going to do this in red, we need to remember to convert it to Kelvin. And to do that, we add 273 to any temperatures that are in Celsius to convert them to Kelvin. And so this will give us the temperature in Kelvin. Now, we know the initial pressure. The initial pressure in this situation is 1.01 atmospheres. So P1 equals 1.01 atmospheres. But we don't know P2. We want to know what is the final pressure. So P2 is our unknown. Okay, so looking at that, we are going to use the combined gas law. We have P1, P2, T1, T2, V1, V2. So using that combined gas law, if we look at that, going back, we said we kept the the volume constant. So if we kept the volume constant, when we rearrange to solve for pressure, we can say since volume 1 equals volume 2, we can kind of take that out of the equation, and really you just have P1 times T2 over T1. And so if we know our original pressure was 1.01 atmospheres times our final temperature, we have our 326.4 degrees Celsius. Make sure you convert it to Kelvin by adding 273, divided by our initial temperature of 24.1, and again, don't forget to add the 273. You get the new pressure, and our new pressure is 200.04 atmospheres. Now, if you look at this original question, it says in millimeters of mercury. So our last step, we found it in atmospheres. Our last step is to convert to millimeters of mercury. And we know from earlier, we said if you have 1 atmosphere, that equals 760 millimeters of mercury. It also equals 760 torr, but we're not asked that. So if you convert that, you get 1,550 millimeters of mercury for your final answer. Okay. Now here's a couple from your homework. We're going to work a few of your homework problems together. If we do them in the notes, you do not have to do them in your homework set. So if we look at number 1, the total pressure inside of a 1.62 liter cylinder. So if we have a 1.62 liter cylinder, what is that? That's our volume, right? So we have V1 there, and it's kept at 35 degrees Celsius. So this is our temperature, our original temperature. And this must be 1.15 atmospheres, must be our original pressure. Okay, so now our volume is going to change. Our volume is going to drop to 0.74 liters. So this is our new volume. So this is going to be V2. And the temperature remains the same. So our temperature is still 35 degrees Celsius. What is the new pressure inside the cylinder? So our new pressure, or P2, is our unknown. Okay, so knowing the things that we know and we don't know, looks like we'll be doing another combined gas law problem. And so if we have the combined gas law of P1 times V1 over T1, and all of that equals P2 times V2 over T2. Looking at what we know the temperature is going to remain the same. So if our original temperature is 35, our final temperature is still 35. If we know that, when we rearrange this to solve for P2, we know our temperatures are going to cancel. So I'm going to go ahead and cancel them now, just to kind of simplify it. So those will cancel out. And really, we're just looking at Boyle's law here. And so if we rearrange this to solve for P2, we'll divide both sides by V2, and we'll be left with something like this. P2 equals P1 times V1 over P2. And if we put in P1, P1 is 1.15 atmospheres. V1 is 1.62 liters. V2, we said, was 0.074 liters. 0.74 liters. All we have to do is do the math. So if we multiply and then divide by 0.74, we get an answer in our calculator. And how many sig figs will we round that answer to? If we look, we have 3 sig figs for that one, 3 sig figs for this number, but this one only has 2 sig figs. So our answer needs to be in 2 sig figs. So if we do P2, our calculator gives us 2.5, our liters cancel, so the unit of that is going to be atmospheres. So we have 2.5 atmospheres for our final answer. Okay, number 2. Go ahead and read that and work ahead of me, and you can, hopefully I'll catch up to you. But the total pressure inside a 2.7 liter cylinder kept at 25 degrees Celsius is 0.85 atmospheres. Suppose that the pressure inside rises to 1.03 atmospheres. We're keeping the temperature constant again. What is the new volume of the cylinder? Okay, so we want to know the new volume of the cylinder. And again, T1 equals T2. Our temperature is constant, so we can kind of cancel out like we did on number 1. Okay. But we do know pressure. We know the pressure and we know the volume before. So if we look at that, we have the volume. So here's V1. We do know the pressure before. This is P1. And we know the pressure after. Here's our P2. Now we can find V2. So writing our ideal gas, or sorry, our combined gas law, I'm jumping ahead of myself. We have P1 V1 over T1 equals P2 V2 over T2. And since we have temperature remaining constant, we can say temperature is not a factor there and kind of simplify it to P1 V1 equals P2 V2. And in this problem, we're looking for the final volume of that cylinder. So to solve for the final volume, we're going to rearrange this. We have V2 equals, if we divide both sides by P2, we get P1 times V1 over P2. And we know P1. P1 is 0.85 atmospheres. We know V1. V1 is 2.7 liters. We know our final pressure is 1.03 atmospheres. So now we know our new volume. If we cancel atmospheres, our answer is going to be in liters. If we multiply 0.85 times 2.7 divided by 1.03, and again, our answer is going to be in 2 sig figs. If we check our starting numbers, we get an answer of 2.2 liters. 2.2 liters is our new volume. Okay, now let's look at number 6. Number 6 says draw a volume versus temperature graph and plot the expected results of heating a gas from 0 Kelvin to 300 Kelvin at constant pressure. So if we have a graph of temperature versus volume, and we keep the pressure the same, if we start at 0 Kelvin, at 0 Kelvin, I'll put a K down here for our temperature. At 0 Kelvin, we have a volume of 0. And our volume is going to increase proportionally. In fact, this is, Charles' law. And so your graph should look something like that. Okay, let's look at number 7. Now, number 7 is not something we've just learned. If we look at number 7, you have 2 identical 1 liter containers. So I have a 1 liter container here, 1 liter container here, and both containers are the same temperature. They're both 25 degrees Celsius. One contains only neon, and neon has a pressure of 1.5 atmospheres. Now the other contains only xenon gas, and its pressure is 1.9 atmospheres. Is the value for the number of moles of neon less than, equal to, or greater than that of xenon, and explain. Okay, what do you think? So if you look at that, xenon is going to have more moles of gas than neon. And if we have the same volume, the same temperature, that greater pressure tells us. Now, how do we know that? Well, Avogadro's principle tells us that if we have equal volumes of different gases, and if they're at the same temperature and pressure, they contain the same number of particles. And so, if we have the same volume in each balloon, the same pressure, the same temperature, they're all going to have the same number of moles. And so we can use that to compare the number of particles if we have different pressures. So Avogadro's principle is kind of useful to us. So let's talk about, when we talk about things, a lot of times for gases, we'll talk about STP. And so STP is standard temperature and pressure. Standard temperature and pressure is 0 Celsius, which is incidentally also 273 Kelvin, and also 1 atmosphere. So that's standard temperature and pressure. Now, when we talk about standard states in thermochemistry, standard states are kind of lab conditions. 1 atmosphere pressure is the same, but we have 25 degrees Celsius. 0 degrees Celsius in the lab is pretty darn cold, but we can do that with gases. Harder to do with things in a liquid state. Okay, so if we have 1 mole of gas, it's going to occupy exactly 22.4 liters of space if it's at STP, standard temperature and pressure. So if you know that the temperature is 0 Celsius and the pressure is 1 atmosphere, and you have exactly 22.4 liters, you know you have exactly 6.023 times 10 to the 23rd gas particles. Okay, so how many molecules would be contained by the air in this room if it was at STP? Okay, so here is an estimate for a room. Here's the volume of the room. If you're in a room that is approximately 12 meters by 17 meters by 2.8 meters tall, the volume in the room is approximately 571,000 liters. How many molecules would be contained by the air in this room? And so if we look at that, if we have this number of liters, if we know for every 1 mole of gas, we have 22.4 liters. And for every 1 mole, we have 6.02 times 10 to the 23rd molecules. How many molecules would be in this room? So if we multiply that through, we get 1.5 times 10 to the 28 molecules of gas in this room alone, if our room had approximately these dimensions. What if we found out that the volume that each molecule takes up is approximately 3.1 times 10 to the minus 27 liters? How much space would those molecules take up? So if we wanted to know that, we could start out with those number of molecules that we found on the last slide. 1.5 times 10 to the 28 molecules in this room. And if 1 molecule takes up approximately 3.1 times 10 to the minus 28 liters of space, we can figure out all of those molecules, how much space do they take up? And if we look at that, they take up about 48 liters of space, which is not very much if you consider the size or the volume of the entire room. So if we figure out how much it actually takes up, 48 liters, what is the percentage of that full entire room? 571,000 liters of space. We find that gases take up approximately 0.008% of the space in a room. The rest is what? Nothing. A vacuum. Okay. How about a couple more homework problems? Let's look at number 10 and number 12. Okay, number 10. We look at number 10. What volume of hydrogen fluoride gas can be produced, in theory, when 234 grams of fluorine gas reacts with excess hydrogen gas at 0 degrees Celsius and 1 atmosphere? Okay, so looking at that, we want to know something about the volume, but here's a little hint. It's reacting at 0 degrees Celsius and 1 atmosphere of pressure. What is that? You see that? Think it's at STP. And at STP, we know the volume of 1 mole of gas at that temperature and pressure. So that's something to kind of look for. But we want to know what volume can be produced when we have 234 grams of fluorine gas. So what do we have here? We have a simple stoichiometry problem. We're throwing in a little bit with what we know about gases. So if we start with 234 grams of fluorine gas, and we're trying to figure out how many liters of HF can be produced. So this is what we're going to, liters of HF. How can we get to liters from grams? So looking at this, our first step, we need to get it to moles. If we have moles of fluorine gas, we can use our mole-to-mole ratio to get to moles of HF. And if we know moles of HF, then we can get, using the fact that it's at STP, to get volume. So if we set this up, set up our T-chart, if we want to get from grams of fluorine to moles of fluorine, we need to know the molar mass. And so if we know for every 1 mole of fluorine gas, we have 38 grams. And all that is 19. It's a molar mass of fluorine times 2 because it's a molecule. So we have 38 grams gives us 1 mole of fluorine gas. Now our next step is looking at the stoichiometry. So if we look at our chemical reaction, we know that every 1 mole of fluorine gives us 2 moles of HF. So if we want hydrogen fluoride gas, we know we have 2 moles. Now we don't want moles of HF, we want the volume. So our next step, if we convert moles of HF to liters of HF, how can we get from moles to liters? Well, we know it's at STP. So for every 1 mole of any gas, not just HF, but any gas, if it's at 0 degrees Celsius and 1 atmosphere of pressure, it takes up 22.4 liters of volume. 22.4 liters of volume. So now we know grams of F2 are converted to moles. Moles of F2 are converted to moles of HF. Moles of HF are now converted to liters, and we have the unit that we're looking for. And so doing the math, solving that equation, we get 276 liters of hydrogen fluoride gas. Down here. 276 liters of hydrogen fluoride gas are produced. Okay. And if you look, if we had easier numbers, couldn't this be a really easy multiple choice question? If the math worked out where maybe this was, instead of 234, maybe we had a round number like 38 grams. That could kind of be an easy multiple choice problem, depending on the numbers you were given. Okay, let's jump down to number 12. What mass of carbon tetrachloride can be produced from 276 liters of chlorine gas and excess graphite? If, again, you're at STP. You're at 0 degrees Celsius and 1 atmosphere, you're at STP. So if I want to know how many grams of carbon tetrachloride, I'm going to write that over here. I want grams of carbon tetrachloride, so I remember where I'm going to. One too many carbons there. Okay, so that's where I'm going, but I'm starting with 276 liters of chlorine gas. So if I'm starting with chlorine gas, if I'm starting with one thing and going to another in a reaction, I'm going to have to go through the mole-to-mole ratio, which tells me step 1 is to convert this to moles. So step 1, I need to go from liters of chlorine to moles of chlorine. Okay, so how can I get from liters to moles? I know I'm at STP. So I know for every 1 mole of any gas at STP has a volume of 22.4 liters. Now if I'm at moles of chlorine, I can get to moles of carbon tetrachloride. So now all I need is my mole-to-mole ratio. So moles of chlorine to moles of carbon tetrachloride. So looking at my chemical equation, I know I have 2 moles to 1, so I have a 2 to 1 ratio. Now my next step, I don't want moles, I want grams. So my last step is just to convert from my moles of carbon tetrachloride. So if I know I have 1 mole of carbon tetrachloride, I can figure out the grams of carbon tetrachloride. And if I do the math, if I add up the molar mass of carbon, which is 12.01, and 4 chlorines, you'll get a molar mass of 153.81 grams. Okay, and so checking, just double checking, I converted liters to moles, knowing that, you know, if you're at STP, 1 mole is 22.4 liters. Next, I use my mole-to-mole ratio to convert moles of chlorine to moles of carbon tetrachloride. And my last step was to convert moles of carbon tetrachloride to grams. Okay, my last step is to multiply everything on the top, divide by 22.4, divide by 2, and hopefully you got an answer of 948 grams of carbon tetrachloride. Okay, now let's go on and we'll get the next biggie. Combined gas law is a biggie, but so is the ideal gas equation, otherwise known as PIVNERT. So PV equals nRT is a really important way to kind of estimate the volume, the pressure, the number of moles, or the temperature of a gas, if you know some of the other factors. Now, something you may have used before, the R value. So Before we used the R value, 8.314 joules per mole Kelvin. We call that the energy R. Whenever we're doing gas laws, we want to use 0.0821 liter atmospheres per mole Kelvin. And how do you know which one to use? Well, you look at your units. When you're working with gas laws, typically you're working with atmospheres. So you want to use this value of R. When you're doing thermo or some other types of applications, if you're using joules, you want to use the energy R, I call it. How do you know it's energy R? Joules are in the units. And so this ideal gas equation will help us estimate, like I said, any of those factors. So if you have an 8.5 liter tank containing helium gas, and we know the pressure is 16.9 atmospheres, and we know the temperature is 25 degrees Celsius, how many moles of helium are available for making balloons? And so if we know this one is the volume, if we know the pressure, we know the temperature, we can figure out how many moles. So we can figure out the number of moles in the tank. So how would we do that knowing pressure, volume, and temperature? Good old Fibner, the ideal gas law. So if we look at that, we want to rearrange that equation to solve for the number of moles. So if we take PV divided by RT, we solve for the number of moles. Now, you are ready to begin substituting in. We know the pressure in atmospheres. We know the volume in liters. So those are good. We can use R. But temperature, we can't use 25. In fact, whenever you get this, I would go ahead and immediately in my notes, I would do temperature equals 25 degrees Celsius plus 273 Kelvin. This is the most common mistake in gas law problems, not knowing how to do it, but forgetting to convert the temperature to Kelvin. So the next step, plug in what you know, remembering to convert to Kelvin. Now, 25 plus 273 equals 298 Kelvin. And so that's where this number comes from. So we have 16.9 atmospheres times 8.5 liters divided by R, which is 0.0821 liter atmosphere per mole Kelvin, divided by 298. And so when we find the number of moles in that tank, we get 5.9 moles of helium in that tank. Let's do another one. Let's do the next part. Part 2, if all of the helium is used to fill 1.5 liter red balloons, and the pressure in there is 0.99 atmospheres, and the temperature is 32 degrees Celsius, how many balloons will you end up with? So how would you solve a problem like that? So what you want to do, so what we would want to do is figure out the total volume with which we could fill the balloons. So we know the pressure, we know the temperature. And I'm going to go ahead and instead of writing this, we'll do 32 degrees Celsius plus 273 Kelvin, which gives us a temperature of 305 Kelvin. So we know the temperature. And let's find the total volume, and then we could divide that by 1.5 liters to figure out how many balloons. So if we're solving for the volume, if we take our ideal gas law, let's rearrange that to solve for the volume. So if we divide both sides by the pressure, we get this equation. Now, we know the total number of moles, we just found that, that are contained in that tank. We know R, and we know the temperature. We know the pressure that the balloons are going to be at. We can figure out what's the total volume available to fill up all those balloons. So if we plug in our 5.91 moles that we found in the problem before, times R, times 305 Kelvin, divided by our pressure of 0.99 atmospheres, we get a total of 149 liters. So 149 liters is the total volume available, divided by the volume in each balloon. So if each balloon had 1.5 liters in it, we would get 99 red balloons. So that's an ode to an 80s song that you may or may not be familiar with. So how about another one? So now the next example, we have an unknown gas. It's collected in 850 milliliter vessel at 1.02 atmospheres and 23 degrees Celsius. It has a mass of 138.45 grams, and the vessel and the gas have a combined mass of 140 grams. Find the molar mass of the gas. Whew. Okay, so that one's a little bit tougher. So let's look at that. If we can find the number of moles, maybe we could figure out the molar mass of the gas. Okay, so step one, looking at what we know and what we don't know. If we know the number of moles, let's find that first. So we know we have a volume, and I'm going to go ahead and convert it just so I don't forget, 0.085 liters. Now I know I have the pressure, 1.02 atmospheres, and I know I have a temperature. Instead of writing 23, I'm going to write my temperature equals 23 plus 273, or what is that, 296 Kelvin. Okay. So if I use my ideal gas law, I want to find the number of moles. Now if I know the number of moles and I can figure out the mass of the gas, I can figure out the molar mass from that. So if I have my ideal gas law, I'm solving for N. So my next step is to rearrange it to solve for N. So if I have N equals PV over RT, my next step is to plug in what I know. So I know I have a pressure of 1.02 atmospheres. I know my volume is 0.85 liters. I know R, and I know my temperature. I already converted that to Kelvin, so we have 296 Kelvin. Go ahead, multiply, divide by everything. Did you get 0.0357 moles? Okay. So that gives us the number of moles. So if I know the number of moles of the gas, and I can figure out by subtracting, I can figure out the mass of the gas. And if I know the mass is, if I know the empty vessel has a mass of 138.45, and then the vessel with the gas in it has a mass of 140.12, I know the difference must be just the mass of the gas. So step two, or the next part of that problem, take the difference of the mass. So I have my mass divided by the number of moles to get my molar mass, or the difference in the mass of the vessel plus the gas minus the mass of just the vessel. That gives me, the difference gives me the mass of just the gas, divided by the number of moles of gas I just found. Okay, this will give me a molar mass of, what did you get? Did you get 46.8 grams per mole? Okay, the next step, the next equation I'm going to talk about is to help us figure out how to find the molar mass of a gas. So, and it's derived from the ideal gas equation. So if we look at this ideal gas equation, if we rearrange that equation, and instead of putting moles, we know moles is mass divided by the molar mass. So if we put that in there, okay, and then we kind of rearrange that equation to solve for molar mass. And if we get molar mass on this side and move pressure and volume underneath, and if we look at this term, mass divided by volume. Mass divided by volume is what? That's density, isn't it? So instead of writing mass divided by volume, if we put density in there, we get what's known as the molar mass kitty cat equation. And again, this one is not on the equation sheet, but here's a way to remember that. I call it the molar mass kitty cat because if we look at molar mass, that equals density, D, times RT over P. Okay, so every good kitty cat puts dirt over his P. So that's a way to remember the molar mass kitty cat equation. So let's use that molar mass kitty cat equation on the next step. You have an unknown gas, and it has a density of 3.24 grams per liter at 1 atmosphere and 28 degrees Celsius. Find its molar mass. Okay, so if you have density and you have pressure and you have temperature, hey, molar mass kitty cat equation. So we know molar mass equals density times R times T over P. So the next step, plug in the density. We know the density is 3.24 grams per liter. We know R. We know the temperature. If we look at the temperature, we had 28 plus 273 to give us 301 Kelvin. Divided by the pressure, our pressure is 1 atmosphere. So when you multiply those numbers, you get a molar mass of 80 grams per mole, which could be useful in identifying an unknown. Okay, so a couple more left. Let's go ahead and get to those. What volume of carbon dioxide can be produced when 68 grams of methanol, CH3OH, burns in air at 25 degrees Celsius and 1.02 atmospheres? Okay, so if you want to know the volume, if you know the number of grams, the first step is going to be to find the number of moles. If you have grams, you're going to go to moles of CH3O2, OH. So grams of methanol to moles of methanol. And then you can go to moles of CO2. Now, once you have moles of CO2, then you can get volume or liters of CO2. So that's kind of how we're going with this problem and how to think about how you get from your starting point to your ending point. So step one, and always, if you don't know what to do, find the moles of something. So step one, find the number of moles of CO2 produced. So If we start with 68 grams, our next step is to convert it to moles, so you need the molar mass. So we know that there are 32 grams of CH3OH for every 1 mole. Now our next step, if we go from moles of one thing to moles of another, this is our mole to mole ratio from the balanced chemical equation. And so looking at that, we have moles of methanol, 2 moles of methanol, CH3OH, to 2 moles of carbon dioxide. So we have a 2-to-2 ratio to give us the number of moles of CO2 produced. So we have 2.1 moles of CO2 produced. Okay, so if we know the number of moles, now we can do that last step. If we know the number of moles, we can get to liters. Now, if we were at STP, all we'd have to do is use the conversion factor. 1 mole equals 22.4 liters. But we are not at STP. How do we know? We are not at 0 degrees Celsius, and we're not at 1 atmosphere. So if we're not at STP, our next step, use PIVNERT. So if I use that ideal gas law, I know the pressure, I know the number of moles, I just found the number of moles, I always know R. I know the temperature, I just have to convert it to Kelvin, solve for that new volume. And so rearranging to solve for volume, I get this rearranged equation. I plug in the 2.1 moles of carbon dioxide I just found, times R, times my temperature, 25 plus 273. So right here I have 298 Kelvin, divided by my 1.02 atmospheres, gives us 50 liters of carbon dioxide formed. Okay. If you have any questions working your problems, send me an email and let me know. Otherwise, have fun solving both your ideal gas equation problems and your combined law gas problems. Bye for now.